Hi, today me and my teammates will be presenting a project titled Parts of Speech Tagging using Dynamic Programming. Can we move to the next slide? So the team comprises of Atharva Sapre, myself Anushka Patil, Sriram Hariharan, and Pareekshit Reddy. The next slide, please. So we'll be going through the introduction, problem statement, the data set that we have used for the project, the methodologies we have used, and comparing the different methodologies along with conclusion and future scope. The next slide, please. So a POS tag is basically a tag that indicates the part of speech for a word within a sentence. POS tagging in itself may not be the solution for any particular NLP problem, but it is definitely a prerequisite to simplify a lot of problems of NLP. It has uses in the following natural language processing task. The first one is text to speech conversion. We need to know which word is being used and the context in which it is being used in order to pronounce it correctly. Then word sense disambiguation. What this means is we need to identify the sense of word, that is the meaning of word that is used in a sentence. For example, she saw a bear. In this sentence, a bear means an animal, which is a noun. Whereas in the sentence, your efforts will bear fruit. Bear, although it has the same spelling, is being used as a verb. Hence, POS tagging is important in word sense disambiguation. Then, in semantic analysis as well, POS tagging is a vital step because we need to understand the meaning or the context in which each word is being used in order to understand the meaning of the entire sentence. Can we move to the next slide, please? So coming to the problem statement, the most fundamental models in NLP are based on bags of words. Bags of words is nothing but it takes into consideration the different words that we have within our corpus and the number of times that they occur within the corpus. So we are not essentially capturing the syntactic relationship between the words here. Building lemmatizers, which are tools for breaking down words to their basic forms, also need POS tagging. POS tagging is basically a process of marking up a word within a corpus to the corresponding part of speech in the sentence, depending on its context and definition. So, our aim here is to build a probabilistic POS tagging model, such as the hidden Markov model, to compute the joint probability of a set of hidden states, which are the POS tags in our case, given a set of observed states. And then we'll be using the Viterbi algorithm, which is basically the dynamic programming part of a project for obtaining the maximum posterior probability estimate of the most likely sequence of hidden states. Can we move to the next slide, please? Pareekshit, sorry. Yeah, the data set. So this project makes use of two data sets, which are from the Wall Street Journal. One would be used for training and the other will be used for testing. The training set will be used to create emission, transmission, and tag count dictionaries, which will be explained further. And the testing set will be used for predicting. Can we move to the next slide, please? Parikshit will be explaining here.
For the baseline model, we've used the brute force algorithm for passive speech tagging. We have computed few dictionaries to help generate the tables, which will help in predicting the parts of speech, which include transition counts. For this dictionary, this dictionary has the values which computes the number of times each tag happened next to one another. Then there is the emission count dictionary. This dictionary will compute the probability of word given its tag. The next one is tag counts dictionary. The dictionary will store tag as the key and number of times each tag appeared as the value. So the workflow of the baseline model goes like this. We will first choose the most prevalent parts of speech for that word in the training set as the parts of speech. Then we would check to see if if this is a match with the actual parts of speech for that particular word. The accuracy of this algorithm can be found out by dividing the correctly predicted words by total number of predictions made so far. The next methodology we used is hidden Markov model using the Viterbi algorithm. The Markov model contains a number of states and the probability of transition between those states. For this project, states are the parts of speech. Markov model utilizes two matrices, transition matrix and an emission matrix. Transition matrix describes the probability of moving from one state to another in the dynamic system. The rows of this matrix are the probability of moving from state represented by that row to the other states. The sum of all the elements in the row add up to 1. The next matrix is the emission matrix. Emission matrix, the number of rows is the number of states and the number of columns are the observation types. We then move on to generate two more matrices, best paths and best probabilities, using the above two matrices. Best path and best probability matrices store the probability of each path happening and the best paths up to that point. The workflow of HMM is we would first generate the emission matrix and transition matrix. Then we would initialize the matrices for best paths and best probabilities. Then we would run the Viterbi forward algorithm to fill the matrices. And then we would run the Viterbi backward algorithm to find the most probable sequence of parts of speech. Let's dive deep into HMM. So after HMM, we would implement Viterbi algorithm, which makes use of dynamic programming. We use transition and emission matrices from HMM to implement Viterbi. This consists of three steps: initialization, Viterbi feed forward, and Viterbi feed backward. Initialization includes, in the initialization step, we would initialize the matrices for best paths and best probabilities that later on we would be populating with the feed forward step. In the feed forward step, we'd calculate the probability of each path happening and the best paths up to that point at each step. For each word, we would compute a probability for each possible tag. Then we would have feed forward, feed backward. The Viterbi backward algorithm gets the predictions of parts of speech tags for each word in the corpus using best paths and best probabilities matrices that we have generated in the previous step. This step returns a list of predicted parts of speech for each word in the corpus. The accuracy for this model can be determined by dividing the correctly predicted words by total number of predictions made so far. From here, my teammate Atharva will take over.
Thank you, Pareekshit. Now I'll explain the working of Viterbi algorithm using an example. So here, let's take an example of the sentence "loss tracks upwards." So there are three words in a sentence, and we want to find the best probable sequence of POS tags for this sentence. So we also have two matrices, best paths and best props. The rows of these two matrices represent the POS tags and the columns represent the words in a given sentence. So the first column represents the starting pointer of the sentence, and thus all the cells in that column will be initialized to 0 for both the matrices. The next column represents the word loss. Now it will refer to the transition and the emission matrix to get the values and fill the cells in the best probability matrix. So for example, the first row in this column will basically be calculated by multiplying the probabilities of the previous tag being the starting pointer and the current tag also being a starting pointer with the probability of this word given the tag is a starting pointer. Now moving on to the next word, tracks. Here we will multiply the product of transition and emission probabilities of the word tracks and the tag starting pointer with the previously calculated values from the previous column. And then we will check which path from the earlier column when multiplied with the product of the current cell gives the max probability. And then we will store the max value in that particular cell. So here the path coming from cell 32 of the previous column gives the max value, and that's why we store 32 in the corresponding cell of the best paths matrix. So while propagating backwards, we can easily traverse to the previous word and its most probable path. And like this, we will fill all the cells and repeat the steps for all columns. And this is how forward propagation works. Now let's move on to the next slide and see the working of back propagation. Here, what we do is we check the last column of the best probability matrix and find a cell with the maximum value. In this case, it's minus 34.99. Thus, we have found the most optimal path of the given hidden states. Here, the word upward has the tag RB. We then look at the corresponding cell of the best paths matrix. So here we have 40, which corresponds to the 40th row of the previous cell, and thus we know that the word tracks has POS tag VBZ. We will then traverse back again to the previous column using the same logic and will land at the 20th row. Now, as we have encountered 0, it means that we have reached the starting of the sentence and hence the algorithm will terminate. So while running this algorithm, we will store each POS tag associated to that particular word in a separate array, which will help us uh, give the most probable sequence of POS tags for a given sentence. So in this case, it is loss being associated to the tag NN, tracks to VBZ, and upward to RB. So this is how backpropagation algorithm works. And these two algorithms, when put together, form the Viterbi algorithm. Now I'll request Sriram to continue. Thank you.
Thank you, Atharva. So we saw a couple of algorithms that we worked out in the project. The first one was a baseline algorithm called the brute force algorithm, which was very primitive in nature, and the complexity of the algorithm was not that much. And the other one was Viterbi algorithm, which used Markov's hidden Markov's model, which also uses dynamic programming. So as we can see, the accuracy metric of the brute force algorithm was 88.89%, whereas the Viterbi algorithm gave us 95.32% for the same data set. By computing probabilities for each of the tags, the brute force algorithm took a longer time because we actually computed the probability of each combination of tags and also words in a sentence. Therefore, we can say that the time complexity of the brute force algorithm was O of n power t, n being the number of tags and t being the number of words. And in comparison with the Viterbi algorithm, which actually goes along the maximum probability branch and it ignores the other branch, so the time taken for the algorithm to run is much lesser, and the time complexity here is O of n square t. Let's move on to the next slide. No, the yeah. So the conclusion is. So here, as we can see, the data set was not much big in our case, but in case of larger data sets, the brute force algorithm is definitely going to take a very large time, and also we have to sort out different methods or more efficient data structure here. But in case of Viterbi algorithm, which is more appropriate for POS taggings because it handles large data set well and it processes the large data set in a much lesser time. POS tagging for large data sets, which gives also better accuracy than the brute force, is any day better than the brute force algorithm. The next slide, please. Yeah. So since we are dealing with an NLP problem here, the most modern technologies that are involved in solving such problems are in deep learning or in neural networks. So one such algorithm is Baum-Welch algorithm, which uses expectation maximization, which calculates conditional likelihood, and but it actually takes a larger time, but then the accuracy is much improved. The other one is transformation-based learning, which is one of the modern methods that we use in POS tagging. It's actually a rule-based algorithm which automatically tags the post for a given text, and it also gives us a readable format uh, of the transformations from one state to another by using transformation rules. And the complexity in tagging is way reduced in TBL as compared to HMM. And also we can use the traditional methods of RNNs and also transformers, which also give a high prediction accuracy, and also takes lesser time. Thank you.